Precalculus. We're skipping chapter 9 because it's got stuff that's not as important for those of you who will be taking the SAT or ACT, if anybody's doing that, in the spring. We want to get to stuff that might be on that test. The stuff on chapter 9 is not. So if there's time at the end of the semester, we'll get back to it. Chapter 10 is on the conic sections. Here we go. The conic sections. This goes back as far as 600 BC as a concept. Didn't start turning into things with equations the way we're going to look at it until the 17th century. So, that's a good 2,000 years later, but they were thinking about it way back in the day. The picture below is called a double naped cone, which I just misspelled. Oh, I'm on fire. I didn't even get to the fourth blank and I already screwed up. Double naped cone. Let's just put that right on top here. We'll just pretend that didn't happen. If you draw a plane that intersects this picture as if like it was, like you were with a saw just going to cut through this three-dimensional picture. The intersection, like once you took it apart and looked at it, will be one of the following two-dimensional figures. A circle, or a parabola, which we have studied before, or an ellipse, which we have not, or a hyperbola, which we have seen before, but we haven't studied to the extent that we're going to at this point. So imagine do your best here to just draw kind of a three-dimensional plane that would go that's parallel to this little horizontal line here. What would happen is if it was just, if it went through and then cut this thing off, it would cut it like this. So I'm going to shade that in so you can see what I'm doing there. And then if I looked straight at that thing, if I took the top off and I looked straight at it, what would it look like? It would look like a circle as far as the outline of it is concerned. Okay, the second one. What if I didn't go parallel? I went through only one of the cones and I went at an angle. What would happen is it would get elongated, right? And so the circle would get stretched in one direction, making it look like an oval, right? Well, we're going to call that in this class an ellipse. Let's see, if I went through here, but I went parallel to this right here, if I went sort of parallel, what would happen is I would hit in one spot and then it would open up as it went in both directions and go across. That's what that would look like right there. That, of course, is our old buddy, the parabola. And then if I sent a plane through here that was perpendicular to this line, so vertical, and I went through and intersected this thing, it would hit in one spot here and become a parabola-looking thing up top. And then down here it would hit and look like a parabola on the bottom. So it would look like two parabolas, one opening up and one opening down. And that, my friends, is a hyperbola. Those are the four conic sections. That's how they were studied originally, as like a geometric shaded in kind of thing. And they looked at the curves and the line segments and all that stuff and the distances and studied it that way. That's only one way. A little bit of a yawn there. Sorry. That's only one way to describe a conic section, or just a conic. We will refer to these things as the conics. The second method for did I just say meth? The second meth. That's not what. That's never mind. The second method for describing a conic will be with a version of the general second degree equation. Okay, now I'm taking that phrase from a different author, a book that we used to teach out of. And this book doesn't really have it named like that. So I'm going to fight the author a little bit this chapter, but I think it's worth it because this is a better way to introduce this material than the way the book does. Okay, this second degree equation goes like this. You ready? This equation is in the book later, so I'm not introducing something difficult for no reason here. Ready? ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Oopsie, longer than that big line that I left there. ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Look what's going on here. You guys have worked with equations where there's an x and a constant and a 0. You've worked with things where there's like a y and a y and a constant and a 0. But you haven't done stuff where there's x's and y's in the same equation. That makes for a new ball game here, right? Brand new ball game. So let's go to page 2 and see what kind of mess we're really getting ourselves into. Okay, the third method outside of that equation for describing a conic will be a description of all points. A collection of a whole bunch of points in geometry is called a locus. The collection of all the points. Like, think of a line segment, for example. Let me just draw a line segment. If you think of how many points are on there, there's an infinite amount of points on that line segment. The collection of every single one of those infinite amount of points is called a locus. Okay, that's the idea there. The third method for describing a conic, besides an equation or a three-dimensional version of cutting a cone in half, it's a collection of all the points that satisfy certain geometric properties. Now, you know the geometric property for a circle. All of these points on the circle are the same distance away from the center. That's a geometric property. An example of this is your first conic definition for the chapter. A circle is the collection of all the points, locus, in a plane that are the same distance from a given point, hk, which is called the center. And that distance, of course, from this point to this little point in the middle of the center, that distance, of course, is called a radius. You've studied all of that before. Now, here's what we're going to do. We're going to derive our first equation using the distance formula because the circle is defined by this distance. The circle, which I could get by chopping that cone in half and taking a look at the cross section. If I cut it horizontal to the ground, the top of it would look like a circle, right? Well, there's a circle, and the definition in geometry is all of these points, this collection of every point that's the same distance away from the center. So here's what we're going to do. The distance formula, taking this from Algebra 1 here, is the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Now you guys know that comes from the Pythagorean theorem, right? Like the distance formula actually comes from the Pythagorean theorem. If you need me to prove that, I can prove that to you at a later time. So instead of x1 and x2, I'm going to say this point is xy and this point is hk, and I'm just going to fill some stuff in here. So look, the distance is the radius. There's an r here, right? So r equals the square root of, I'll go with this first, x, and then minus h. X minus h squared. Okay, and if I went x first, I'm going to go y first, so y minus k squared. All right, if I don't want that square root in my formula, I square both sides, and look what I get. R squared is equal to x minus h squared plus y minus k squared. And ladies and gentlemen, we have our first equation that we can use to plot the points to graph a circle for a conic section. So our first definition of a conic section by equation, not by geometry, goes like this. A circle is the collection of all points, locus, in a plane that satisfy the following equation in standard form. X minus h squared plus y minus k squared is equal to r squared, where the point hk is definitely the center of the circle, and r is the radius of the circle. Oh, we are moving now. Not one sine or cosine or tangent to be seen. You got to be loving that. Let's go to page 3. I got to keep my stuff organized over here. All right. Lots of examples on this page, clearly. Rewrite the equation of the following circle in the form of the general second degree equation, just so you see what it looks like. Okay, so I'm going to make up an equation. X minus 3 squared plus y minus 1 squared is equal to 4. That's the equation of a circle. Let's just break this down for a second, okay? If it goes x minus h squared and y minus k squared, and hk is the center of this circle would be at hk, which it goes x minus h, so that would be 3, and it goes y minus k, so it would be the 0.31 is the center. And the radius, well, if r squared is equal to 4, then the radius has to equal 2, doesn't it? So from this equation, I can quickly find the center and the radius, and I could graph this thing if I wanted to. But that's not what I was asked to do. I was asked to write it in the form of the general second degree equation. What does that thing look like? Go back to the first page. It looks like that. Okay, so here's what I'm going to do. I'm just going to multiply all this stuff out. And then let me go back to this equation one more time. Everything's on the left side, and then there's a 0 on the right side. So watch. I'm going to go x minus 3 times x minus 3 and multiply it out. You're good at that. And then plus y minus 1 times y minus 1. You're good at that. And it's equal to 4. Okay, this is x squared. It'll be minus 3x minus another 3x. That's minus 6x. It'll be plus 9. Then after that, I got a plus sign. Y times y is y squared. And it'll be minus 1y and minus another 1y, so minus 2y. And then negative 1 times negative 1 is plus 1. And then I'm going to subtract this and put this over on this side of the equation because I'm supposed to have a 0 over there. Multiply that out, bring that on over. Now it goes in the order. Let me bring this thing over here one more time. Look at the order we went. X squared goes first. If there was an xy term, it would go next. There isn't one. Y squared is second. So the two squareds go first. Then the x, then the y, then the constant. Okay? X squared. Then there's the y squared. Look for all the x's I can find. There's just one, so it'll go minus 6x. Then find the y, it's minus 2y. Then put all these together. 9 plus 1 is 10. 10 minus 4 is 6, so it's plus 6, and it's equal to 0. So these are two equivalent forms of the equation of that circle. This is the general form, and again, I don't think the book uses these terms, but I'm gonna because I think it's helpful, and this is the standard form. Standard form helps us graph things. General form helps us compare things. We've played this game before. All right, next one, example. The point 1,4 is on a circle whose center is at negative 2, 3. Write the standard form, that one, standard form, of the equation of the circle. Okay, well, let me just write the standard form. X minus h squared plus y minus k squared is equal to r squared. Now, if I have the center, which I do, I can just put those two numbers right in here. And if I have the radius, which I don't, I can just put it right there, and then I'm done. I wrote the whole equation. I don't have that, but what I do have is a point, which is an x and a y, right? Isn't that an x, and that's a y, and that's an h, and that's a k? So I'm just going to put all four of those things in here, and we'll be able to solve for r, then we can write our equation, right? So x is 1, minus h is minus negative 2. That means plus 2, doesn't it? And then y is 4, and it's going to be minus negative 3, which means plus 3. All of that is equal to r squared. So 1 plus 2 is 3 squared. 4 plus 3 is 7 squared. All of that is equal to r squared. 9 plus 49 is equal to r squared. So r squared equals 58. That means the radius is whatever the square root of 58 is. But I don't care because it didn't ask me to do anything with the radius. It just asked me to write the standard form of the equation. So here we go. That's not the word 50. That's the word so. That's not 50 is not a word. It's a number. I'm so dumb. Anyway, x minus h squared plus y minus k squared equals r squared. I have everything I need now. I have my center. So I'll be able to go x. Instead of minus negative 2, I'm going to write it plus 2 squared plus y, instead of minus negative 3, I'm going to write it plus 3 squared is equal to r squared, apparently, is 58. There you go. I took a point and a center, I put them where they belong, found r squared, wrote my equation. Okay, here's where you might get a little mad. I'm going to say a phrase you're not going to enjoy. I've already said this phrase once. You actually got pretty good at this in the first semester. This says rewrite the following equation in standard form. X squared, I'm a little hesitant to even say this word out loud because you're going to have an emotional reaction to me saying this word out loud. So brace yourselves. We're going to get that to look like that. We're going to have to we're going to have to complete the square twice. Okay, so I'm going to go over here and I'm going to put the x stuff together in parentheses. X squared minus 6x, and remember this, you leave the third spot open. Then I'm going to put plus, and I'm going to go y squared, and I'll find the y part, it's plus 4y, and you leave the third spot open. And then I'm going to just take this 8 and put it on the other side. Because look, you end up with a number over there anyway, so constant just goes over there. Okay, do you remember how this goes? You take half of this, which would be -3, and you square it, and you put it in that spot. That's how you create a perfect square. You take half of this, which is 2, and you square it, and you put it in that spot. And you have to make up for whatever you put there by either subtracting it after or just do the same thing to the other side of the equation. Well, fortunately, we're moving things onto the other side of the equation, so whenever I add, I just add. Okay, so that part is actually going to be a little bit easier this time around. So here we go. X squared minus 6x, this will be plus 9. And this will go y squared plus 4y, and it'll go plus 4. I had a -8 there, and I have to make up for this one, so I have to put plus 9. Whatever I do to one side of the equation, I do to the other side of the equation. And if I added 4 here, I have to also add 4 there. This one turns into x minus 3 squared. This one turns into y plus 2 squared. And this turns into, let's see, -8 plus 9 is 1, plus 4 is 5. Look at that. You just completed a square twice, and you didn't even have to throw up or anything. I'm so proud of you. Now, what I could do with this kind of thing is I could say, here's an equation, change it to standard form, name the center 3, -2, name the radius square root of 5, and graph it. We could do all of that. All of that. All right, let's go to the last page. Oh, looks like we are going to graph. Hey, that's fun. Now, rewrite the following in standard form. Okay, here you go. X squared plus y squared plus 8x plus 7 equals 0. I kind of want to just turn the camera off and have you try this one on your own, but it's a little funky because there's no y. It actually makes it easier. So let me show you what happens. Ready? I put all the x's together. X squared, then there's a plus 8x, and then you leave an empty spot, and you put all the y squareds together, but there's just the y squared. There's nothing else to put with it. That 7 goes on the other side of the equal sign. So look, I'm not going to have to do anything with the y's this time. That's kind of nice. So half of this is -4. Oops, it's not -4. It's just 4. And we square that, and we put it here. And whatever we add here, we have to add there. So here you go. X squared plus 8x plus 16 plus y squared, just sitting there by itself like a loser, is equal to -7 and then plus 16. Okay, so this turns into x plus 4 squared, and then here's y squared, and then this is equal to -7 plus 16 is equal to 9, and so I'm actually done. I could just circle it. There's the equation. It doesn't look very pretty with all those spaces in there, but x plus 4 squared plus y squared equals 9. All right, your last example for the day. And then I have a wonderful surprise for you. You're going to be very excited about this. Now that you're so emotionally distraught after completing the square for a third time, I have a wonderful surprise for you. Ready for this? Here we go. Sketch the graph of the circle. Well, the center, which is HK, is going to be its x minus h. So basically, when you go to get numbers out of here, it's, again, you've done this before. It's the opposite of what you see. If it's supposed to be x minus h, and that's a -4, that had to come from x minus -4, didn't it? So x minus h, so this has got to be a -4 here. And then for this, if this is supposed to be y minus k and there's nothing there, that means that it's 0. So the center is at -4, 0. And the radius, well, the radius is just the square root of 9. R squared is equal to 9, so r equals, I guess, plus or minus 3. But we never call a radius a negative. That's silly. So I'm going to go -1, 2, 3, 4, and put my point right there. That's the center. I'm going to go 3 in every single possible direction and find the locus of all those points and draw it. It'll be a circle. So here's the easiest way to do that. Go up 3, 1, 2, 3. I lost count. I lost count on the way to 3. That's funny. 1, 2, 3. 1, 2, 3. It's a little harder to go on a diagonal and count 3 because it doesn't really work that way. So that's going to be good enough for me. And I'm going to sketch my circle just like that. Sketch your best circle, you know. All right. Oops, I lied. There's one more example. Find all x and y intercepts for this circle with this equation. Well, at least I'm going to be nice and put it in standard form. I could give you that ugly, monstrous general form, make you complete the square twice before you even start the problem. But, I mean, what kind of loser would do something like that? Hint, maybe on the test. So, find x and y intercepts. This is not this equation, right? Like, that's a different equation. It's not that circle. How do you find x intercepts? Well, if you look at this one, this doesn't have a y-intercept, but it does have x intercepts. So what I would do is, wherever there's, let's just count, okay? This is negative 1, 2, 3, 4, 5, 6, 7. There's the point negative 7, 0 on here. Notice the y is 0. So if I wanted to find this, I would put a 0 right there and solve the rest of the equation, right? Okay, so I would put a 0 in for y if I want x-intercepts. So look, here we go, x-intercepts. I'm going to find those first. That means that y equals 0. So put a 0 in for y and just solve. It goes like this, x minus 4 squared plus, if I put a 0 in here, I have negative 2 squared, and it's equal to 16, right? So that's a 4. Negative 2 squared is 4. And when I subtract 4, I'm going to get 12. So x minus 4 squared is equal to 12. Then, of course, I would take the square root, and when I do, I get x minus 4 is equal to plus or minus the square root of 12. Kind of unfortunate that's not a perfect square. That would be nicer if it was. But I do know that that's 4 times 3, so it's 2 root 3, right? So this ends up being x equals, I'm going to add 4, and I get 4 plus or minus 2 root 3. Okay? For the y-intercept, well, if I want a y-intercept, that means that x equals 0. So you put x equals 0 into the equation, and you solve. Here we go. Put a 0 in here, and you have negative 4 squared. 0 minus 4 is negative 4 squared, plus y minus 2 squared, and it's all equal to 16. Okay, 16 plus y minus 2 squared is equal to 16. So when I subtract that, I actually get something kind of easy. Y minus 2 squared is equal to 0. So that when I take the square root here, which is the next step, I don't need a plus or minus. It's just y minus 2 is equal to plus or minus square root of 0 is just a fat 0. And when I add 2, I get y equals 2. Okay, so my intercepts, since it asked for them, there could be 4 of them altogether. I have 4 plus, this is, if I got an x, it's going to be 4 plus 2 root 3, comma 0. Be much easier if I made that a decimal so I could see where it is if I had to graph it, right? And then, of course, there's going to be 4 minus 2 square root of 3, comma 0. And then this one where y is 0, that means y is 2, that means x is 0, so there's another point at 0, 2. There are your 3 intercepts. Now that was not your happy bonus having to do all that algebra. Your happy bonus at the end of these notes is the fact that my math lab and this book don't even teach the circle part of the conics. They just skip it as if you're a bunch of chumps that don't need to talk about circles. So as a result, you guys, you're not going to believe this, but my math lab has no homework problems for circles. You have no homework today. So we will start with parabolas tomorrow, and my math lab definitely has homework for parabolas. It will be very similar in feel to this. The definition of a parabola that you've never heard before has to do with distances, just like this one has to do with distances. So it will have equations, just like this has equations, and you can write it as the general form, just like that. And we will graph things, we will solve things, we will complete the square, and so it'll be very similar. So today was a warm-up. You got to learn about circles. There is no homework. Enjoy your day.